self-biasing circuit of FET. The requirement of two supplies as in fixed biasing circuit is eliminated by using self-biasing circuit. Here that is a self-biasing circuit is present, coupling capacitors C1 and C2 and resistance RD RS. The coupling capacitors at the input and output are open circuited under DC bias conditions. So the Ig is equal to 0 ampere of FET. The drop of voltage across the RG, it is Ig RG, it is Vg equal to 0 RG, Vg is equal to 0 volts. The circuit is redrawn for the DC analysis. It is of this forms: VGS the circuit is redrawn for the DC analysis as RD VGS RS. For the DC, applying KVL at the input minus VGS minus VS, it is equal to 0. Applying KVL at the input, VGS is equal to minus ID RS, because IS is equal to ID for these circuits. So that the input voltage VGS depends upon the output current. The input voltage VGS is not fixed in magnitude as in fixed bias circuits. So that ID is equal to IDSS into bracket of 1 minus VGS by VP whole square. It is equal to IDSS into bracket of 1 plus IDRS by VP whole square. This AX square plus BX plus C, that is the equation is of quadratic form. Solving for ID, then VGS is determined. Applying KVL at the output circuits, so that plus VDD minus IDRD minus VDS minus VS, it is equal to 0. VS is equal to ISRS is equal to IDRD, because IS is equal to ID. VDS is equal to VDD minus IDRD minus IDRS. VDS is equal to VDD minus ID into bracket of RD plus RS. VDS is equal to VDD minus VDD minus ID into bracket of RD plus RS, because IS is equal to ID. ISRS and is equal to IDRD. Because the here ISRS is equal to VS is equal to ISRS is equal to ID RS. So that VDD minus IDRD minus IDRS, so that VDS is VDD minus ID into RD plus RS, so that VDS is equal to VD minus VS, VS is equal to VD minus VDS. VDD minus IDRD, VGS is equal to VG minus VS, VGS is equal to minus VS, because VG is equal to 0. Graphical analysis. The intersection of the transfer curve and the network curve gives the quiescent values of the drain current IDQ and gate to source voltage VGSQ. The transfer curve for the FET can be drawn by the given values of IDSS and pinch off voltage by using the shorthand methods. So that by using shorthand methods we shall draw the transfer curve. The network curve can be drawn by using the equation VGS is equal to minus IDRS. Here the network curve can be drawn by using the equation VGS is equal to minus IDRS. 2 points are to be determined when ID is equal to 0 ampere, VGS is equal to 0. Another point is when ID is equal to IDSS, 2 VGS is equal to minus IDSS upon 2 into RS. Here the transfer curve, here it is the transfer curve IDSS upon 2, IDSS upon 4. Here this one, and here it is the another point, and here it is another point. That is this one it is transfer curve, and here it is a network curve. So that the straight line joining these. The straight line joining these 2 points intersects the transfer curve at the point Q. The points of intersection is the point of intersection is the operating point or the quiescent point. The quiescent values of drain current and gate to source voltage are determined. That is the intersection of the transfer curve and the network curve gives the that gives the operating point or the quiescent points. The quiescent values of the drain current and gate to source voltage VGSQ are determined. That is, they determine the following for the network as shown in the figure, so that we here the VGSQ, IDQ, VDS, VS, VG and VD. This one, it is a self-biasing circuit, so that here IDSS given 8 milliampere, pinch off voltage minus 6 volts or 3.3 kilohms, and from that one here the VGS ID by using shorthand methods, so that the VGS is equal to 0, ID is equal to IDSS, and the IDSS by 2, VDS is equal to 0.3 Vp, and here the IDSS upon 4, that is 2 milliamperes, it is 0.5 Vp, and IDSS it is equal to 0, ID is equal to 0, it is equal to pinch of voltage 6 volts, so that here this one it is transfer curve, and VG from that one the network curve to draw the network curve can be drawn from equation VGS is equal to minus IDRS, and ID is equal to 0, VGS is equal to 0, ID is equal to IDSS upon 2, 8 milliampere upon 2, 4 milliampere, it is VGS is equal to minus 4 volts. So that here we have got the 2 points, one is 0, another one it is 4 volts, so that the point of intersection, if these 2 points, the point of intersection of these 2 curves, it is used the operating point, so that the values of the point of intersection of the transfer curve and network curve is operating point Q, so that the values of VGSQ at operating point is equal to minus 2.6, and the drain current is 2.6 milliamperes. VDS is equal to VDD minus ID and RD plus RS. VDS is equal to 20 minus 2.6 10 raised to 3. VDS is equal to 20 minus 8.82. VS is equal to IDRS is equal to ISRS is equal to IDRS is 2.6. VG is equal to 0. VD is equal to VDD minus ID RD is equal to 20 minus 20 minus 2.6 into 10 raised to minus 3 into 3.3 10 raised to VD is equal to 20 minus 11.42 volts. Voltage divider biasing circuits. The here R1, R2, RD, RS, A bypass capacitors, these are the coupling capacitors, and input voltage is applied at the input, and here we will be getting the output voltage applied. Here the coupling capacitors at the input and output are open circuited for DC analysis, so that the bypass capacitor is also open circuited. The circuit for the DC analysis is shown in the figure. Here the voltage V, the circuit for the DC analysis, it is shown as shown in the figures, because the coupling capacitors are also open circuited, bypass capacitor is also open circuited, so that the voltage VR2 is equal to VG, so that IG is equal to, and IG is equal to 0, IR1 it is equal to IR2, so that the IR1 it is equal to IR2, VG is equal to VDD R2 upon R1 plus R2. Applying KVL at input plus VG minus VGS minus VS is equal to 0. If KVL is applied at the input here, plus VG minus VGS minus VS, it is equal to 0. VGS is equal to VG minus VS. VS is equal to ISRS is equal to IDRS, because IS is equal to ID. IS is equal to ID, so that VGS is equal to VG minus IDRS. VGS is equal to VG. IS is equal to VS is equal to ISRS is equal to IDRS is equal to, because IS is equal to ID, so that VGS is equal to VG. VGS is equal to VG minus IDRS. VGS is equal to VG minus IDRS. The equation is the equation for a straight line. The points on the straight line can be determined by when ID is equal to 0, VGS is equal to VG, and VGS is equal to 0, ID is equal to VG upon RS. So that the points of intersection of transfer curve and network curve gives the operating point or the quiescent point Q. So that here the VGSQ and ID. The transfer curve it is of this from the shorthand methods. Network curve it is when the ID is equal to 0. When ID is equal to 0, VGS is equal to VG. That is positive values. VGS is equal to VG. And VGS it is equal to 0. ID is equal to VG upon RS. T is equal to VG upon RS. So that the point if a straight line is drawn through passing through these 2 points, then that straight line it intersects the transfer curve at these points. So that applying KVL to the output circuit plus VDD minus VDS minus IDRD minus ISRS it is equal to 0, because IS is equal to ID, VDS is equal to VDD minus VDS is equal to VDD minus ID into bracket of RS plus RD. S is equal to VD minus VS, so that VD is equal to VDD minus ID RD. So VGS is equal to VG minus VS, VS is equal to ID RS. Determine the following for the network, so that is IDQ and VGSQ, VD, VS, VDS, VDH. Here 2.1 megohms, 270 kiloohms, for 2.4 kiloohms, 1.5 kiloohms. IDSS is equal to 8 milliamperes, pinch of voltage minus 4 volts. So that here the transfer curve is VGS and ID, IDSS upon 2 upon 4 0. A straight line equation for the voltage divider circuit is VGS is equal to VG minus IDRS, and VGS it is equal to 0, ID is equal to VG upon RS, so that ID is equal to 1.214 milliamperes. VG is equal to VDD into R2 upon R1 plus R2 upon 16 1.82 volts, because VGS is equal to VG minus IDRS and VGS is equal to 0 ID. Because this one it can be drawn from the shorthand methods, that is ID, VGS and the ID 4 milliampere or 2 milliampere 0, IDSS upon 2, IDSS upon 4 and 0. Here it is 0.3 Vp, 0.5 Vp and Vp, that is pinch of voltage. Okay. Here now when ID is equal to 0, VGS is equal to VG equal to 1.82 volts. So that the transfer curve it can be drawn, and the network curve it can be drawn from the values of ID and the VGS. So that ID is equal to VG upon the RS and VGS is equal to VG if these 2 points a straight line is drawn passing through these 2 points, so that will intersect the transfer curve at these points, that is the gives the quiescent values of VGS and ID. IDQ is equal to 2.4 milliamperes and VGSQ is equal to minus 1.8 volts. IDQ is equal to 2.4 volts and VGSQ is equal to minus 1.8 volts. VD is equal to VDD minus IDRD is equal to 16 minus 2.4 into 2.4 into 10 raised to 3, 10.24. VS is equal to IDRS is equal to these values, that is 3.6 volts. VDS is equal to VD minus VS, VDS is 6.64 volts. VDG is equal to VD minus VG, it is of this value. VDG is equal to 8.42 volts. The small signal analysis of JFET. Small signal parameters of JFET are GM, it is transconductance, small RD, it is the drain resistance. Gm is equal to delta ID upon delta VGS at the Q point, and small rd is equal to delta VDS upon delta ID, and VGS it is equal to constant. Gm is equal to delta ID upon delta VGS at the Q point, dID upon dVGS, d upon dVGS IDSS into bracket of 1 minus VGS by VP whole squares. Because from Shockley's equation ID is equal to IDSS into bracket of 1 minus VGS by VP whole squares. IDSS into bracket d upon dVGS 1 minus VGS by VP whole squares. IDSS into bracket of 2 into bracket of 1 minus d by dVGS of 1 minus d by dVGS of VGS by VP. 2 IDSS into bracket of 1 minus VGS by VP minus 1 upon VP. 2 IDSS upon modulus of VP into bracket of 1 minus VGS by VP. Gm it is the transconductance, so that 2 IDSS upon modulus of VP into bracket of 1 minus VGS by VP. The magnitude of modulus of VP is taken for Gm is to be positive. So that is taken. The maximum value of Gm is Gm0 when VGS is equal to 0. Gm and VGS is equal to 0, Gm0 is equal to IDSS upon modulus. But maximum value of transconductance. Drain resistance RD delta VDS upon delta ID is equal to constant. Small signal model of JFET is the input voltage, output voltage. Here input voltage in the VGS, and here it is the current Gm VGS, and here small RD, and from that one gate, drain, and source. The small signal analysis of fixed bias configuration of JFET is the coupling capacitors C1 and C2. The coupling capacitors C1 and C2 at the input and output terminals are short circuited for the small signal analysis. The coupling capacitors C1 and C2 at the input and output terminals are short circuited for the small signal analysis. The biasing voltage VGG and the supply voltage are short circuited. The biasing voltage VGG and the supply voltage VDD are short circuited. The biasing voltage VGG and the supply voltage are short circuited. For coupling capacitors are short circuited. The bias supply and the biasing voltage and the supply voltages are also short circuited, so that if it is replaced by an equivalent small signal model. Here input voltage, here it is output voltage, and here it is RG input resistance, but here this one it is the small signal model of whatever here JFET it is drawn. A input voltage VGS, a current source Gm VGS, and a resistance RD. A small resistance already in parallel with this current source. So that is here also the JFET is replaced by a small signal model with an input voltage at the input and a current source and a resistance RD, and whatever this RG and RD are the biasing resistances present in the biasing circuits. So that the JFET is replaced by an equivalent small signal model. RG and RD are biasing elements at the input and outputs. Gm VGS is a current source directed from drain towards the source. Gm VGS is a current source directed from the drain towards the source. The input impedance Zi is equal to Rg. The output impedance is determined when input voltage is equal to 0. The input voltage is equal to 0, that is Vi is equal to VGS, and that is the Vi is equal to Gm VGS, it is equal to 0. Output impedance is determined when the input voltage is equal to 0, when input voltage Vi is equal to 0. Input voltage is equal to 0 and Vi is equal to VGS is equal to Gm VGS is equal to 0. The current source is open circuited at the outputs. The current source it is open circuited at the outputs. The output impedance is equal to small Rd parallel capital Rd, that is the output impedance. If the small signal parameter small Rd, that is the it it is greater than the 10 RD, then output impedance is equal to capital RD. Z0 is equal to capital RD, because RD, small RD is greater than or equal to 10 times the RD. Now voltage gain EV, applying KVL at the output is minus GM EGS into bracket of small RD parallel capital RD, so V0 is equal to 0, minus GM EGS into bracket of RD small RD capital R of D, drain small, that is small single parameters, and here it is drain resistance, it is equal to 0, but input voltage Vi is equal to VGS, so that voltage gain is output voltage upon input voltage minus GM into bracket of small, that is the small signal drain resistance and biasing resistance RD. So that if small signal drain resistance is greater than or equal to 10 times the drain resistance, then voltage gain is equal to minus GM the biasing drain resistance. That is when the small signal drain resistance is 10 times greater than 10 times the RD. The fixed biasing configuration had an operating point defined by VGSQ is equal to minus 2 volts, IDQ is equal to 5.625 with IDSS is equal to 10 milliamperes and VP is equal to minus 8 volts. The network is applied with an input signal of Vi as shown in the figure. The input voltage Vi, coupling capacitors and a 1 mega ohm gate resistance 2 volts, coupling capacity C1, C2, drain resistance 2 kilo ohms, and this one it is the fixed biasing circuits. IDSS 10 milliamperes, pinch off voltage equal to minus 8 volts. Network with an applied signal Vi as shown in the figure. The value of YOS is provided as 40 microsiemens. Determine GM, RD, input impedance, output impedance, determine voltage gain, determine current. Voltage gain, ignore the effect of small. GM0 is equal to IDSS upon modulus of VP. GM0 is equal to into 2.5 millisiemens. GM is equal to GM0 into bracket of 1 minus VGS by VP. 2.5 is equal to GM is equal to 1.87 millisiemens. Small RD is equal to 1 upon YOS 1 upon 40. RD is 25 kilo ohms, and ZI is equal to RG is equal to 1 mega ohm. Input impedance is equal to RG is equal to 1 mega ohms. Output impedance is equal to small RD parallel RD is equal to 25 10 raised to minus 3 a 2.3, it is equal to, that is the 1.85 kilo ohms. Voltage gain minus GM into bracket of the small, that is the small signal drain resistance, and here it is biasing resistance RD is equal to minus 0.85, voltage gain minus 3.5. Voltage gain when the small signal drain resistance is greater than or equal to 10 times RD is minus GM RD. Voltage gain is equal to minus voltage gain when the small signal drain resistance greater than or equal to 10 times the RD, voltage minus 3.74. Design the fixed bias circuit as shown in the figure to have an AC gain of 10, that is determine the value of RD. Here you have to design this fixed biasing circuit for and determine the value of RD. So that here the biasing voltage VGSQ is at ground potential, so that VGSQ is equal to 0 volts. Here it is the circuit it is given, and for that circuit we have to design this fixed biasing circuit and determine the value of RD. SS is 10 milliamperes and VP minus 4 volts by OS is 20 microseconds. Here GM is equal to IDSS upon modulus of VP 1 minus VGS by VP. GM is equal to GM0 into bracket 1 minus VGS by VP, and VGS is equal to 0 volts. Not is equal to IDSS upon VP 2 into 10 raised to minus 3 upon 4 is equal to GM, because GM 5 milliseconds is equal to GM0 is equal to 5 milliseconds GM, because VGS the voltage gain of fixed, because when VGS is equal to 0, when VGS is equal to 0, GM is equal to GM0. When VGS is equal to 0, GM is equal to GM0. So that the voltage gain of fixed biasing configuration of FET is voltage GM, that is small signal drain resistance, and the parallel combination of drain biasing drain resistance. And RD is equal to 1 upon YOS is equal to 20 into 10 raised to minus 50 coulombs. So that it is the output short circuit, that is output admittance. Here small signal voltage gain is equal to 10, so that 10 is equal to 5 into the 5 into 10 raised to minus 3, it is the transconductance. Here 50 into 10 raised to 3 into parallel capital RD. So that from this one, if the value of RD is determined, it is equal to 2.08 coulombs. So that the approximate standard value of the resistance is RD, that is the biasing drain resistance. RD is equal to the 2 kilo ohms.